Problem 2, one more application about the activation of the target. Here we have a stable aluminum target is bombarded by incident particles to create sodium 24 unstable element. And you know this element will decay again, and we have a relation between the rate of production of Na24 A0 and the rate of decay, the activity A, which is equal to 1 minus exponential lambda t. Okay, you know A equals to lambda n, decay rate or activity, the number of decay per second. A0 equals to nr, the rate of production of unstable element, 1 minus exponential lambda t. You don't need to calculate this expression each time you want to solve a problem. You can put it directly. Okay, let me see what we have. What is the fluence rate? When I say fluence rate per centimeter square per second, I mean the flux. I want to find the flux, which is equal to the number of incident particles n0 divided by A and time. Okay. First of all, we have 1 m curie of Na24. When I say curie, it means activity. You know, 1 curie equals to 3.7 times 10 power 10 BQ. You have to use a unit BQ, becquerel, for the activity. And here we have production activity. When I say production activity of unstable element, it means A0, okay? We have A0 equals to 1 m curie, which is equal to 1 times 10 power minus 3. Curie equals to 3.7 times 10 power 10 BQ. Okay. Okay, I repeat, production activity, it means A0, because I product the unstable element of sodium 24. Okay, we have a target section, I mean A. Okay, the section, you know, if we have the section facing to the incident particles, this one is A, which is equal to 1 centimeter square. And we have a mass of the target aluminum equals to 1 gram of aluminum. Okay, I give you the cross-section of production. I mean the nuclear cross-section, because we have barn, okay? I give you, you know, 1 barn. Here you have to convert the unit. 1 barn equals to 10 power minus 28. Okay, let me put it in centimeter square, because I am using centimeter square, equals to minus 24 centimeter square, 1 barn. So here we have a nuclear cross-section equals to 20 millibarn. So we have 20 times 10 power minus 3 times 10 power minus 24 centimeter square. So I want to calculate the activity produced at the end of the irradiation. What is the activity at the end of irradiation? I mean A, because N here equals to NR divided by lambda, 1 minus exponential minus lambda t. You know, N is a number of unstable element at the end of irradiation. We have the incident particles will bombard the aluminum, and we are creating a new unstable element of sodium 24. at the end of the irradiation, we have n number of unstable element. Okay, so here we can say A is the activity at the end of irradiation at a time t, and A0 is the initial activity of creation of unstable element. Okay, so I give you here the activity. I want to calculate the activity at the end of irradiation. It means I have to calculate A or lambda n. Anyway, at a period and so on. Let me start. First of all, we have sigma, we have to calculate flux. So we have to find the relation between sigma, flux, mass, and so on. If you come back to the table, here in this table, we have the relation between, for a one slab, look, here we have sigma equals to n of interaction times A divided by n target times n0. Okay, so we can write here, we have sigma equals to n interaction times A divided by n target times n0. Okay, and don't forget, n interaction, I mean delta n. Okay, and you know, an interaction, I mean, for each interaction, for each nuclear reaction, we have a new unstable element. We talked about this. The rate of interaction is the rate of production of unstable element. So an interaction divided by time, by t, by time, which is equal to nr, the rate of production of unstable element, which is equal to A0. All the time, NR is A0, is the activity of production of unstable element. Okay, I give you its value, which is equal to 1 times 10 power minus 3, 3.7 times 10 power 10 BQ. Anyway, here I want to calculate, you know, we have to calculate phi, the flux. Let me simplify this one. You know, here we have sigma, which is equal to nr. We can say here we can divide n interaction. We can say n interaction divided by t. And here also we have n target divided by t. Okay, I divide by t up and down times n0. Okay, and here we have a. So you know, n interaction divided by time, n interaction divided by time is A0. We can say here is the activity of production equals to A0 times, we can say times A. And you know, here we have n target, n0 divided by t. We can say here n0, this t, we can put it up here. So we have A times t divided by n target times n0. You know, n0 divided by at, n0 divided by at is a flux. So here we can say equals to A0 divided by n target times flux phi. Okay, So here I need to calculate the flux. So I used this relation to calculate the flux. We can back to this one. We can say flux equals to A0 A0 divided by sigma times n target equals to we have A0 and sigma also we have its value, but n target, you know, if you come back also to the table, we can calculate n target. Look here, we have n target equals to m divided by molar mass times Na. Okay, so we can say here equals to m divided by molar mass m times Na. Okay, we can put m here, molar mass, which is equal to 27 of the target. When I say target, I mean the aluminum, Al equals to 27, about 27. Okay, now we have all the values. We have to substitute its value here to calculate the flux. So we can say here, you know, the flux, it must be in atoms or particles per unit centimeter square and second. So here we have, we must have particles per unit centimeter square times second. Okay, A0 equals to 1 times 10 power minus 3 times 3.7 times 10 power 10 BQ. You have to say becquerel. When I say BQ, you know the unit of BQ is particles per second. Okay, we can say here BQ, it's equivalent to particles per second. Also, okay, here we have 10 power 10 BQ times m is the molar mass of the atom, which is equal to 27, divided by sigma 20 times 10 power minus 3 times 10 power minus 24 centimeter square, and the mass equal to 1 gram. Okay, times Na, you know, Na equals to 6.020. Okay, let me calculate the. So we do the calculation. We must have flux and particles per centimeter square times second. The answer will be, I want to calculate it. So the answer will be phi equals to 8.29 times 10 power 10 particles per centimeter square times second. Okay, this is the value of the flux. The second point, I want to calculate what would be the activity produced at the end of irradiation. I said before, the activity produced at the end of irradiation will be A, which is equal to A0 times 1 minus exponential lambda t. Okay, I need to calculate A. You know, I give you a period, in the case of a period t half, and I mean I want to calculate the activity after, because you have a creation of unstable element, and this unstable element will decay to a stable element after the end of the irradiation. So I need to calculate this value of activity at a period, at a time of period equals to half, or at a time equals to half lifetime. So I want to calculate A, first of all, if T equals to 1 period, and you know that period equals to 15 hours equals to 1 times 15, we have to put it in second, equals to 60, 60 times 3600 to get the answer in second. Okay, this is T. So we can substitute the value of T here. Anyway, we can say A equals to A0, 1 minus exponential. Lambda equals to ln 2 divided by 1 period. Okay, times the time. The time here I give you 1 period. So we can eliminate T half and T half. We get here the activity at this time equals to A0 times 1 minus exponential minus ln 2. Okay, we have the value of A0. We can calculate the value of the activity will be in particles per unit time. Okay, this is the value of the activity at a time of 1 period, of 1 half time. Okay, the second part, I want to calculate the activity at a time equals to 0.1 the period. 0.1 the period. So we can apply the same calculation, which is equal to 1 minus exponential minus lambda. Lambda equals to ln 2 divided by t half times a time equals to 0.1 t half. Okay, we can eliminate again t half and t half, and we can calculate its value, which is equal 1 minus exponential minus ln 2 times 0.1. Okay, you calculate its value also in atoms per unit time. Okay, like this you have to understand the application of all these parameters in the case of the activation of a target. In the case of the activation of the target, you have many expressions you have to respect. If you come back to the table, I classified all these expressions of the activation of the target.